All right, recorded is rolling. Today is Wednesday, October 5th, and we are officially kicking off the next unit today. Now, there's going to be a few topics that kind of fit together. All right, we're going to be looking at, well, today, centripetal force. I'm going to have you guys do a lab to uncover a formula, an expression. Okay. Now, centripetal force is a force that holds something in a circle, which it's sort of hinted at all along the semester, but we haven't exactly addressed. You guys remember how the law of inertia tells you that objects either want to stay at rest or move in straight lines, right? And if something is not doing that, either it's speeding up or slowing down or going around a curve, the only reason that would happen is if there's some kind of outside force on it. Now, we've addressed speeding up and slowing down over and over, right? So like speeding up, slow down, type of acceleration from a net force. But what we haven't quite addressed, and we're going to start today, is this idea of, well, what keeps something like on a curved path, right? What's something like turning, okay? And that needs a force too. It's a special kind of force called centripetal force, which is provided by some force. In this case, like a hanging weight is going to provide a tension, and the tension is going to hold us in a curved path. Okay, guys, can I see that? Okay, so we've got that idea. In the next few days, I'll also talk to you guys about universal gravitation. So two masses will gravitationally attract to each other. And then we're going to put those two ideas together and make orbits. Okay, so over the next few weeks, this is what we're looking at. Okay? School stuff. You guys know that the end of the quarter is in a couple of days. You guys have a take-home quiz, right? You guys have take-home quiz, right? So some of you guys have already turned in a take-home quiz. You guys know I found you guys some homework too, but we've gone over all that. So here, let me make just one all video for all my classes. For my conceptual students, we had this packet of 60 questions. We've done all of those. For my honor students, I picked a bunch of problems up. This chapter 4, chapter 5 from the honors textbook. We did a bunch of those. Okay, so between those and the take-home quiz, sometime this week, I need those pages. But Friday's like a hard deadline because that's the end of the quarter. Okay, and there's no school Monday. Also, 1 week from now, Wednesday is going to be a weird day because there's PSAT. I've been slated to proctor that. You guys are going to be relocated somewhere. Where? I don't know. I don't have that information yet, but that's all coming up. All right. You guys good with the general school stuff? Okay. So big picture, where you are, what's going on. All right. Now, the specific labs. Oh, let me show you guys the actual apparatus so you guys know what this cartoon version of it refers to. You guys see this PVC pipe right here? PVC pipe? Hey, there's the PVC pipe. You guys see this red string? Hey, there's like a string that's connecting. What's at the ends of the strings? Ooh, look, a couple of Play-Doh canisters. You guys get Play-Doh canisters today. You guys see these? Okay. Hey, look, there's a couple of Play-Doh canisters. You guys see all this? You guys get so far? Okay, guys that? All right, and what I'm gonna do is just wheel this around in a circle, right? Exactly like you see in this picture. And I'm gonna do that off camera here. So if you're watching the video at home, so I'm just gonna do this just live demo in class. Okay. Oh, look at that. Look, you swing around in a circle, just like that. Okay, so that's the basic setup right there. Okay, now let's play around with this a little bit. Suppose I swing this kind of slowly. Okay, ooh, look at the size of that circle. So real tiny circle. What if I speed up a little bit? Can I set up a little bit bigger circle? Oh, look at that, it's a bigger circle, right? I'm holding the size of the circle constant at some point. Right? Oh, but hey, I can change the size of the circle if I want. Look, it's an even bigger circle, but now I'm holding it constant again. Okay, you guys see that? Okay, okay, so playing around some variables there. Okay, and it's sort of addressing this last question here. It's like, well, if I change the speed, how does that change the radial size of the circle? Sort of just did that with guys, right? But you know what else is probably at play? Is what about the mass of the swinging canister, or what about the weight of the hanging canister, right? Like the reason they're canisters is because here's why they're canisters, because you can pop these things open. Oh, look, little lab weights. This guy says 20 grams. So if I add 20 grams to the 6 grams, because an empty small canister is 6 grams, right? The standard size is about double that. The little tiny 6 grams. Right? Is this about 26 grams going on right here? About 26 grams, right? I can like double loop this string. Right? And that's not coming off right there. If you think it might, just want to throw some tape on, right? So it's like super secure. All right. Right. So canisters, you can add lab mass or weight to those. Right. All right. So big picture, there are ultimately 4 variables that we're juggling. 4 variables. Right. Here's what they are. there's the mass of the swinging canister, right? How much mass is this, right? That's being pulled into a circle, right? Now, what's pulling it into a circle? Well, it's the tension in the string, which is provided by the weight of the hanging canister. And each of these canisters, sure, has a mass and a weight, but I care about the mass of the swinging one and the weight of the hanging one. You guys got that? Right? Those are different physical properties, right? Mass is like inertia measured in, well, we're going to use grams today, grams, okay? And weight, can we measure like newtons? We're going to use millinewtons today, right? Scale down everything by a factor of 1,000, right? Okay, so we got those. You could set up circles of different sizes. So that's radial size, rate is the curvature, right? Some circles, some size, right? And there's going to be some speed, some instantaneous speed that's going to put everything into equilibrium. Well, I should tell you, the bottom canister will be in true static equilibrium, right? The weight down and the tension up is going to just hold it right in place. But the one that's swinging around will not be in true equilibrium because it's on a curved path, right? Now, you might hear the term like dynamic equilibrium. That's to say like this radial size isn't going to increase or decrease, it's just going to stay on the circular path, right? But there will be a net force, and the net force is the tension, which again is equivalent to this weight, right? Provided by this weight. Right, you guys see that? I wonder how these four variables are related. Four variables are related. Like if you change one of these, something else is going to shift, right? Well, there's some formula, there's some expression that ties these all together, and you guys got to figure it out. But you guys know in science, ideally, if you can, you just have one independent variable and one dependent variable, right? But we have four variables, so how are we going to do this? Well, we're going to control two variables at a time and then change out one and let the other change, right? And since I kind of know how this goes, I'm directing you guys. Here, here's what we're going to do. You guys are going to be in 3 different groups. So each group is going to get a third of the story. You guys are going to get all your data today, and then tomorrow, well, I'm going to open up an Excel page and we'll put all the data together and we're going to make some graphs. We're going to answer this question. We're going to make a formula. This is going to be like a master formula. Okay. So everybody's going to get a third of the story today. Okay. Okay. So, let's break out these pages right here. Okay. So some of you guys have just a blank table. Let's take a look at what this is. Let's go across the table. Okay. So first column says mass hanging. Right, so the hanging mass, that could be in grams. Right? Now, you guys know normally in this class we use kilograms, right? So grams is like 1,000th of that. So the empty canister is a few grams. You can stack glad masses in it, add those to it. There's a scale back there. There's a balance if you want to like get it more accurately. Right? But I don't really care about the mass of the hanging one. I care about the weight of the hanging one. Guys, how do you go from mass to weight in the metric system? You just multiply by what? 10 meters per second squared? Because that's Earth gravity, right? Okay. Now that could be true from kilograms to newtons, but that's also from grams to millinewtons because everything's just scaled down by 1,000. Right. So, for example, suppose the mass of the hanging one is like 21 grams. Right. Just make up a number, 21 grams. What would the weight be in millinewtons? 210 millinewtons. Right. Just multiply by 10 meters per second squared. Right. Here. You guys good? Right. All right. Next column. Mass swinging. Some of these, by the way, you'll see are bold. You guys see bold? That might indicate some kind of independent variable, right? So mass swinging. How about the mass of the swinging one in grams? You guys could record that number, right? Next column says 1 over the mass. Just do a calculation. That won't make sense yet, but it'll make sense by the end of this lab. Next column. Ooh, another bold variable. Radius measured in meters. Do you guys think you could set up like a circle, constant size, and then hold a meter stick right up here and get a pretty good idea what the radial size is? Might be like, for example, if this is like 70 centimeters, could you call that 0.70 meters? You guys can do that, right? 0.70 meters, right? You record that number, right? Next column, just take the reciprocal of that. That'll make sense later, right? Time 10 and time 1. So I'm gonna have you guys do 10 revolutions and then divide by 10. Here, let me break out the equipment again. So if you're watching this video off camera, I'm gonna do a quick demo again. Okay. Oh, by the way, while I'm doing this demo, let me point out something that there's a really common mistake, and I want to clear this up. Okay. Because here's the thing with this lab. If you guys are really careful with your measurements and you do everything exactly right, then we're going to get some really nice graphs tomorrow. And this equation is going to pop together really nice. On the other hand, if you're really sloppy with keeping the radial size the same or timing it, or you make the mistake that I'm about to show you guys how to do, then the graphs aren't going to make any sense. Right? So if you do everything right, though, it's going to work out really nice. Okay. Guys, when this thing's going around in a circle, right, constant size circle, at some constant speed, right, are you going to grab this bottom Play-Doh bucket like and hold it in place with your hand? No, right? You're just going to let its weight naturally provide the force that is the centripetal force that's going to hold everything together. See, if you grab it with your hand like or if you pinch the string to the PVC pipe, then you're providing an external force that's going to throw everything off, and your numbers aren't going to make any sense, right? I mean, the purpose of having just one hanging is that you can know what its weight is, and that will be the centripetal force. Isn't that true? Right. All right. So here, having said all that, let's do this off camera here. Let's set up. Right. So here's how I'm timing this. Ready? And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See, I counted 10 revolutions. You guys know you're going to start with 0, right? You're going to go 0. Whoever has a stopwatch is going to hit start. Right. And then when you hit 10, you stop the stopwatch. Let's say, for example, I'm just going to make up something. Let's say that came out to like 7.5 seconds. Right? Could you do time for 10 revolutions is 7.5 seconds? Right? But really, you care about the time for one revolution. So what would the time for one revolution be? Would it just be a tenth of that? Right? So 7.5 divided by 10 is 0.75 seconds. Right? Does that make sense? Right? Now, why? Why am I having, why not just do one and go like, start or stop? Why do 10 and then divide by 10? What's that good for? How about like reducing random error, right? One of the biggest errors you'll have just in general in the labs in this class is figuring out exactly when to start and stop the stopwatch. But if you do 10 cycles, like 10 revolutions, and then divide by 10, that error also gets divided by 10, right? Right. So we've addressed all these variables except for one, and all of you are going to have to. It's just going to go this way, right? That's how this works out. V, the speed. Right. Notice I'm not saying velocity, I'm saying speed because it's always changing direction, right? But the speed might be constant or pretty close to it. Right. So, hey, speed, could that be distance divided by time? Right. And hey, what is the distance around one circle? There's a name for that. It's called the what? Distance around one circle starts with the C. Circumference. And what's the formula for circumference in terms of radius? Circumference equals 2 pi r. You guys remember that? Circumference equals 2 pi r. Okay. And by this point, you will have known what the time for one revolution is, because that's t sub 1. Right? It's 10 cycles divided by 10. Right. So this column right here says v, and what's this little expression right underneath the v? Equals 2 pi r divided by t1. Hey, that is distance divided by time. That's circumference divided by the time for one revolution. You guys see that? So won't that give you the speed? Right. And the very last column says to square that speed. That won't make sense yet, but that'll make sense by tomorrow. Okay. Right. So for example, if it's 7 meters per second, 7 squared is 49. Can you guys do that? Okay. Good so far? You guys all right? Okay. All right. Now, you probably don't have a paper that looks exactly like this. You probably have a paper that has some hash marks in it. Right. You guys see that? Because it goes back to this idea that there are 3 different setups. You guys are going to get 3 different perspectives, controlling 2 variables at a time. Okay. So let's suppose we start with let's start with this one. Okay. So about a third of you have a paper where the hash marks are kind of in the middle. Okay. See where it says weight hanging and it's blank all the way down? That means you'll have different weights, different hanging weights. But you're controlling for the swinging mass and the radial size. So if you have this exact paper, then the swinging canister, you don't touch the entire lab, the entire day today. You just leave it sealed. And the size of the circle, you're going to whatever circle you set up, you're going to use the exact same size circle over and over and over again. Right? You guys got that? But you're going to change the hanging weight. Right? Maybe like add weight as you go along. Right? Let's do some hypothesizing. Okay. If you increase that weight, that hanging weight, do you think you'll have to swing faster or slower? You think faster? That's a pretty good hypothesis. I wonder exactly how faster. I wonder if you triple the weight, it's going to be triple the speed, or it's going to be less than triple or more than triple. You can find out, right? But you see, you'd be controlling for. See, if these 2 are your variables, independent, dependent, then these 2 are your controls, right? Right. Okay, so that's the first star. That's this first star right here. Right. That aligns with this paper. Next paper, you might have one with the split hash marks. Guys see it? Split hash marks, and there's an open set of columns in the middle. Right. So there you're controlling the weight hanging and also the size of the circle again, but you're changing out the mass of the canister that's swinging. That's it. So it's pretty similar idea to what we just did, but except we're changing out this canister, right? So here's your independent variable, dependent variable, and then these two guys are your controls, right? With the split hash marks, right? Guys, go there. Okay. And if you don't have either of those, then you probably have a paper that looks like this, where all the hash marks are on the left side. Guys, yeah. If you have this one, then you're leaving the two canisters untouched the entire time. So once you have them sealed and ready to go, then you can just tape them shut, right? But what you will be changing is the size of the circle. Can you guys do that? Right. So if you have all the hash marks on the left side, right, which is this third star right here, then the mass swinging and the weight hanging are controlled. And you might start with a small circle and they get bigger, bigger, bigger circles. Oh, I forgot to hypothesize on the last one. Guys, if you have a, go back to the last paper with the split hash marks. If you have a heavier swinging mass, should you swing faster or slower to maintain the circle size?
Faster.
I'm hearing a little bit of both. Let's figure that one out. Okay. And then on the one where we switch over to where all the hash marks are on the left side, where you're just going ahead and leaving the two canisters sealed. As you make bigger and bigger circles, do you think that's going to correspond to a faster or slower speed? Right. So go ahead and hypothesize to yourself what that'll be. Right. So you're going to have one of those three papers, right? And in fact, if you ended up with a blank paper, that's kind of like a wild card. You could just jump in any group, right? You guys get that? Okay. All right. So, I also want to mention these graphs at the bottom. All right. So depending on what group you're in, what paper you have, you'll be able to do some graphs, but not all the graphs. See how some graphs are completely blank? If it's completely blank, that means you have enough data to do whatever the title says. If it has a little message in gray that says borrow data to complete this graph, that means that by the end of today, you personally won't be able to make this graph, but tomorrow, I'm going to pull up an Excel page and I'm going to have you guys volunteer your data. And then we'll make all the graphs tomorrow. Okay. All right, there's more graphs on the back. And that all leads to, a couple of boxes at the end, which is going to be able to answer this question. We're going to come up with an expression that relates these four variables. We're going to come up with a physics formula for centripetal force. That is the ultimate goal. All right, who's got any questions? Any questions? All right, everything you need is back in the lab tables. I will walk around and help you guys out.